Okay, first law of thermodynamics. Before we get into that, talk about the zeroth law, just really quickly. If you have three systems, they can be metal blocks, they could be containers of water or some solution, but they're in thermal equilibrium. That means that you set them next to each other and allowed them to touch and exchange heat till they have hit some equilibrium. Then TA equals TB because they're right next to each other. And then, so the temperature of A is equal to the temperature of B. So if that's true, and if the temperature of B is equal to the temperature of C, then the temperature of A is equal to the temperature of C. Now that seems quite obvious, but we often have to state things like this so that we know that that's what underlies everything that we do, and that's why it's the zeroth law. The first, second, and third laws were already in place when it was realized you need to state this. This needs to be stated, and the reason is that if you're going to study thermodynamic systems, you need to study temperature. And if you're studying temperature, you're using some sort of temperature gauge, often a thermometer, and that's the easiest one to understand this law with. So if you have a thermometer, you have a solution, you have it. You put the thermometer into a solution. You have the glass of the capillary that makes up the thermometer and encloses the mercury. So the temperature of the mercury. So we put it in, let it reach equilibrium. The temperature, I should go from the other route, let's go over here. The temperature of the solution, it should be in thermal equilibrium with the temperature of the glass, so they should have the same temperature. The temperature of the glass is equal to the temperature of the mercury, so the temperature of the solution is equal to the temperature of of mercury, which means that thermometers work. If that weren't true, then we couldn't use thermometers. We couldn't measure heat or any kind of temperature gauge, so we couldn't measure heat. So we couldn't do any kind of work at all using in thermodynamics. We couldn't trust anything. So, but you might say that, well, this looks obvious, but you think about it, when we're looking at a thermometer and we're saying that we're measuring the temperature of a solution, we're not. We're looking at the temperature of the mercury. That's what you're measuring. But with the zeroth law, we can be confident that if we are measuring the temperature of the mercury, we're also measuring the temperature of the solution. So very important. Seems trivial, but it is extremely important to do any kind of work in thermodynamics. State the first law of thermodynamics in your own words. Well, here's the equation. So you can just state the equation. It's the change in internal energy of a system is equal to the heat that comes in or goes out of the system plus the work that is done on the system or by the system. So this is also basically the law of conservation of energy. The first law keeps track of all the energy that's used in any system. So here, what is the difference between a state function and a non-state function? A state function depends only on the initial and final states of a system. Does not depend on the system's history. If you fill up a burette and the volume starts out, the initial volume is 0, and you fill it up to, you put in 35 mils, then your change in volume is VF minus VI, which is going to be 35 minus 0, or 35 mils. Now, how long did it take you to put the solution in? Did you use your left hand or your right hand? Were you standing or were you sitting? Doesn't matter. None of that matters. It doesn't matter if it took you 15 seconds to do it or 15 hours. in the end, the volume was 35 mils. So it's independent of the history. But something that is not a state function, like Q, that depends on the history. For instance, if you travel up to, from wherever you are to Imlay City, that distance that you covered on a map, not on how you travel, but on a map from wherever you are to the Imlay City, is the same distance no matter how you got there. But how you got there will tell you how much heat you used up. So, or in other words, how many calories you burned. If you walked, that's going to be different than if you ran, or if you sat in an air-conditioned limo, or if you used a pogo stick. If you used a pogo stick to go from, say, where I am in Troy up to Imlay City, you'd have burned several tens of thousands of calories to get there. Whereas if you sat in an air-conditioned limo, hardly any. So Q, the heat and work, depend on the history of the system. So three state functions would be volume, temperature, and pressure. We also have enthalpy, internal energy, and entropy and free energy that we'll see later. But two non-state functions would be heat and work. Those depend on the history, how you went about doing what you were doing during the change or during the process. All right, now a gas is enclosed in the cylinder piston system, so you have this container with a piston in it, and you can put a plunger, make it a plunger, but let's just have it sitting there where we know that this is going to be able to move up and down pretty freely. Then we put in, on top here, we put in a block that's 5.50 kilograms, and that pushes down on the plunger, on the piston. It does work on the system. Since it's doing work on the system, the work is going to be greater than zero. If the system does work on the surroundings, so if it pushes up, then the work is going to be negative. And same with heat. When heat flows in, that's going to be a positive value, and if heat flows out of the system, a negative value. So you should keep those terms in mind. That was discussed in Chapter 6 some time ago, 1170. Now we're going to use this equation from Chapter 6 as well. The work is going to be equal to the mass times the gravitational acceleration of the Earth times the height change, or the change in height. So as the mass is put on there, it's 5.50 kilograms. The acceleration, 9.81 meters per second squared, is the gravitational acceleration of the Earth. And then the change in height is 0.35 meters. We want to make sure we're in the right units. This comes out to be 18.9 joules. Kilograms meters squared per second squared are joules. And then it says at the same time heat evolved. Q, heat evolved, that means it left the system, so it should be negative. And then the internal energy is Q plus W, so Q is minus 2.50. Make sure I'm on. Yep. And positive 18.9 joules. So you should know the positive and negative signs for heat and work, how they work, what happens to the system during those processes, negative and positive. I should finish this up. This is 16.4 joules. Okay, and then let's do another one here. In this case, we have a plunger system where the mass is taken off. We remove 2.5 kilograms. That's taken off, so the plunger moves up, so that means the system does work on the surroundings, so the work is going to be negative. And we can make this, just going to leave it as height, but it should be the change in height. We'll just leave it as the equation. So it's just, we're always interested in the difference in a process. So the piston went up 0.15 meters. And that came up to be negative 3.68 joules. They say that the heat was absorbed, so 4.50 joules of heat was absorbed, so that's a positive. So the internal energy, the change in internal energy, and note that change there, that's what we're, as I said, we're almost always interested in the change overall for whatever state function we're dealing with. And then just put these guys in. And this comes up to 0.820 joules. Okay, what is the relationship between enthalpy and heat? Delta H is equal to the heat at constant pressure. Because in most of our situations that we're going to come across in the lab, we have constant pressure. Because we have all of our beakers, flasks, burettes, everything is opened up to the atmosphere. So we assume, unless a huge storm is coming in very quickly, that the atmospheric pressure doesn't change very much during a reaction that we're dealing with. Now, before we do the next part, so we can see that we've changed one of the values here for the first law. Assuming that we're at constant pressure, then we can change to this. So, sure that's on there. So we changed that. Now we're going to change the term for work, because work, we can just state what the number of joules, but often we're dealing with a system, a mechanical system, and we know what the equation is for work. Like we did, the last one was mgh, but that's not the normal one we're going to be using for our gas systems. Here's our problem that we're going to have here. We're going to be looking for what is the change in the volume for the combustion of 1 mole of methane at 25 degrees Celsius in 1 atmosphere. What is W? Okay, so first thing is let's change the equation, that term for work, into something we can use for this gas system, and it's going to be a very common one that we'll be using. So work is force times distance. And for us, we're going to be talking about, should make this round here, we're going to be talking about a system that, a reaction in which takes place inside of a piston, cylinder piston container, so that this piston can go up or down, and so that we can get a change in height, which is going to be related back to a change in volume. So we can first do that. Say this is the work that's going to be done by our chemical system here, producing gases or using them up. It's going to be negative force times the height, but more to the point, the change in height. And the change in volume is going to be equal to for this system, it will be the area of the piston, because the whole cross-sectional area is going to be the same if it's going to be able to move up and down, times the change in height. So the change in height is going to be the change in volume over area. We do this because we're interested in the change in volume rather than the change in height, because we can use the volume in our gas laws. So there's nothing wrong with stopping here, but it's not going to help us as much as changing over to volume. Now, if we rearrange this a little bit, we get this form, and the force over area is the pressure, and we're going to assume that's constant. And if we do that, then our internal energy, which is Q plus W, at constant pressure, then that's going to be delta H minus P delta V. So at constant P. So if we know the delta H, which that was given in that problem, and P delta V, then we can solve for delta U. So let's look at and they want us to do all of these things. So the combustion for methane is this. And we have to look at the gases. We have 3 moles of gas to 1 mole of gas. And so let me just write that, 3 moles. This doesn't count because it's a liquid. And what we're guaranteed is at 25 degrees Celsius and 1 atmosphere, which is where we are, that the 1 mole of gas equals 24.5 liters. Now, if we were at different temperature and pressure, we'd have to use the ideal gas law to determine the volume, but luckily we don't have to do that here. So the change in volume is going to be V final minus V initial. V final is 1 mole of gas, it's a 1 mole of gas, so that's going to be 24.5 liters. And then the initial was 3 times that. So this comes up to be minus 49.0 liters. The volume dropped, so it's negative. And we can also change this to cubic meters because we're going to need to do that to solve for the work. So the work is equal to negative P delta V, and the pressure we are unfortunately going to have to go to pascals. Those are the SI units. Pascals times meters cubed will give us joules. So we have to make sure that we use the pressure as 1.01 times 10 to the 5th. It's actually 101,325 pascals, but we changed over to this. And this is negative. And this comes up to be, because there's a negative and a negative, 4,949 pascals meters squared, or meters cubed, which will be joules. And we can change it to 4.95 kilojoules because we're going to need to. All right, now, so that's our work. Our heat is delta H, and they gave us delta H, minus 890.2 kilojoules. So delta U is going to be Q plus W, going to be negative 890.2 kilojoules. And then we have plus 4.95 kilojoules. And so this comes up to negative 885 kilojoules. And that is the guy. Now I'm going to put one up here. I'm going to have to do this very quickly because we don't have a lot of time. So, oops, not sure if I have it at all here. So the formula is sodium carbonate, which is a aqueous, plus 2HCl, aqueous, goes to CO2 and water, plus 2 sodium chloride aqueous. So delta V is going to be a change of 1 mole. There's no gases here, so it's going to be positive. So we're going to go up by 22.5 liters, or 0.0225 meters cubed. So the work is going to be negative P delta V. So it's going to be negative. The value is going to be negative this time because this is a positive value when the volume went up. And you can work this out the way that I did it previously, a little slower, but I just want to get another problem in here before the end of the video here. So this is 2.27 kilojoules. And then delta U, which is going to be delta H minus P delta V. This is going to be minus 665.5 kilojoules minus 2.27 kilojoules. This comes up to be minus 6.68 kilojoules. So you can see that if you make a mistake on the sign, that's going to really change the answer. So be careful about that.